Hi class, welcome to Online EdVantage. I'm Dr. Scott Adamson, and before we even start, would you please subscribe to our channel? Now, in this video, we're going to continue with the idea of line integrals, but in certain situations, you can compute a line integral without parameterizing the curve. Now, this isn't a universal thing. It depends on the context. You'll have to decide which strategy you're going to use, but I want to just share with you and develop with you the idea behind the line integral without parameterization. Now, to do so, let's generalize this whole idea. Here's the point. First, you have a vector field. A vector field is you input a coordinate like x comma y in a two-dimensional graph, and you output a vector. So that vector is going to be defined by some function. We're going to have some function of possibly both x and y that'll generate the I component of that vector. You'll have maybe another function of x and y that'll generate the j component of that vector. So you have this vector field. Then, through that vector field, you have a curve. Now, when the curve is parameterized, that curve will have an x component, which will be some function of t, the parameter t, for the I component. And then the y component, y will be a function of t, the parameter t, as the j component of this parameterized curve or vector value function. So, in general, vector field, parameterized curve. Now, to get the line integral, the first move we make is like a composition of functions. We want to make sure that as we live in this vector field, we want to stay on the parameterized curve. So we're going to insert into the vector field the parameterized curve. So where we had p for any xy, we're now going to isolate ourselves to be only on the parameterized curve. So it's going to be p of x of t, comma y of t, I. And then likewise, our q function will be kind of focused in on that parameterized curve, x of t, y of t, j. Now we sometimes simplify this and just call this piece, just call it f. Now remember, ultimately we're going to dot f with dr. So we need dr. And dr, now it's really dr dt. We're just going to multiply the differential dt to the right side. So keep that in mind as we go. So to get dr, we'll take the derivative of the components of this vector value function. So the derivative of x of t will be dx dt. And the derivative of y of t will be dy dt. And then the dt, the differential dt, we move it over to the right side. So here's f, here's dr. Our next move is to dot them. Now, just for notational simplicity, let's call all of this p of x of t, comma y of t, let's just call it p. In fact, I'll write it here. We'll say we have pi, and let's just call all of this q plus qj. So we're going to dot pi plus qj with our dr. Now keep in mind when we do the dot product, it becomes a scalar, very important piece here. The scalar that we obtain with this dot product is found by multiplying the I components. So we'll have p times dx dt. We'll have q times dy dt. And then remember, we have that differential dt. So here's f dot dr, but let's go ahead and simplify f dot dr. If we were to multiply all of this out, the differential dt's would eliminate, and we would have p times dx plus q times dy. Now, the beauty of this, now we'll do an example in a minute, but the beauty of this is this dot product now can be left in terms of x and y. We don't need the parameter t anymore. That's going to be the beauty behind this. The strategy behind this is computing a line integral without parameterizing. Now wait, there's still one more step though. Once we have this dot product, we need to sum up along that curve C from whatever interval from A to B, whatever that limitation will be in a particular case. We're now going to integrate that dot product P dx plus Q dy. Now if that restriction is known, we'll have an integral from A to B of P dx plus Q dy. Now I know right now it's just kind of a bunch of alphabet soup as we work through the steps here to get to this form, but I wanted you to see where this P dx plus Q dy is really originating from. But let's go apply it now back to the problem we did in the previous video, just to make the connection on how this thing will be applied. So we're going to apply this non-parameterized version of the line integral to the problem we did in the last video, just so you can see that it does work out the same. It computes the same value. We had this vector field, yi minus xj, along this parabolic path just between x equals 1 to 2. And remember, when we looked at it graphically, it seemed obvious that the collection of dot products, the accumulation of dot products, would result in a positive result. In fact, it was 19/3 or 6 1/3. Let's apply this version of the line integral to that same problem and see that it works out the same. So the line integral f dot dr from A to B can be applied without parameterization by taking p times dx plus q times dy on that interval from A to B. Now look back at your work from our generation of this formula. P was the horizontal or the I component within our vector field. So P is going to be y. So it's y dx plus Q. Q was the j component from our vector field. So negative x dy. And we're going to run this thing from 1 to 2. Now, at this moment, it might feel a little bit awkward. You know, you have y dx, you have negative x dy, we've got x's and y's kind of mixed up here, but that's okay. We have some definitions that we can take advantage of. Definition number 1, y is defined by our curve to be negative x squared plus 4. So instead of y, we're going to say negative x squared plus 4 dx. Now that should make you feel a little bit better that we have now an integral all in terms of x. Plus this negative x, fine, but then dy. Let's do a little bit of work and find out what dy would be. Now remember, y is equal to negative x squared plus 4. Therefore dy, or think about dy dx, we're just going to again move the differential dx to the right side. Dy would be negative 2x dx. So we're going to replace dy with negative 2x dx. So let's simplify and see if you recognize the result. So we're going to integrate from 1 to 2. We've got negative x squared plus 4. We've got plus negative x times negative 2x. That would be positive 2x squared. And rather than put dx in both places, we'll just kind of factor out that differential dx to get it to be in a more familiar single variable integral format. And if we simplify one more time, notice negative x squared plus 2x squared would be positive x squared plus 4 dx. Now, if you look back at the previous video where we parameterized the curve and applied our line integral, we ended up with the same result. So, of course we do, because that's what the math shows us over here, but I just wanted to convince you that we're going to end up with the same result without parameterizing the curve. And this integral, again, you can check it out if you like. I won't go through all the steps this time, but this integral does turn out to be 16/3, or not 16/3, 19/3, or 6 1/3. So we can, in certain cases, we can compute line integrals without parameterizing the curve. Now, as we continue, you're going to see more strategies for computing line integrals. And at the end, we'll kind of sum it all up and you'll see under what situation should you do this strategy or that strategy. You'll have to learn which strategy is applicable in what context, but keep watching, you'll see.